And we are recording now. Okay. I'll go ahead and start with the introduction.
Okay, can you hear me?
Yes.
Yeah, good afternoon, everyone. Welcome to the Geospatial Forum. I'm Ross Meentemeyer, Director of the Center, and it's a real pleasure to have Anthony Calamito with us today to share what he's been working on. Anthony serves as the Vice President of Products for Enview, where he helps define requirements and capture feedback to ensure software solutions meet customer needs. So this includes lots of things, as he tells us, like providing feedback to engineering, ensuring customer success, optimizing go-to-market to maximize brand awareness. And doing all this, he has over 16 years of experience in the geospatial industry, a majority of which has been supported by supporting the defense and intelligence community. He's co-founded the Geo 261, a consulting firm, to help customers understand and apply location-based technologies and tradecraft best practices to meet mission needs. So in the past, Anthony's had a number of exciting leadership roles. He's been the director of government programs at Mapbox. I know many of you know lots about them. The chief geospatial officer and VP of products at Boundless Spatial, now Planet, and solution engineering lead at Esri. Really quite a repertoire of experience. Anthony is also a fellow with the American Geographical Society and a former steering committee member of Location Tech. Also very dear and special to us, Anthony kindly serves the Center for Geospatial Analytics External Advisory Board. He's a native of New Jersey, where he studied geography at Penn State, and though we're lucky now that he calls North Carolina home. So welcome, Anthony.
I appreciate that, Ross. Thank you very much for the warm welcome. It's been an interesting year, I think, for all of us, to say the least. And I think these offer a real good opportunity for us to stay connected and offer up an opportunity to continue to pass on information and learn from each other. So I very much welcome the opportunity to chat today. I believe I have the ability to share my screen here. I hope, can you see that, Ross?
Yes.
All right, perfect. Let me, whoops. Okay, so without further ado, as Ross said, I'm Anthony Calamito. I do serve as the VP of Product for Enview. Enview is basically a 3D AI company, and we'll talk a little bit about what that means and how that plays into today's discussion a little bit later on. As Ross said, I do also sit here on the External Advisory Board at NC State for the CGA. I'm very excited to share with all of you today some, call it insider baseball, some knowledge about how different organizations are using AI, machine learning, computer vision, HPC, and what we call live location data to really modernize the way we think about mapping. Unfortunately, we're going to basically just scratch the surface today. I wish we could deep dive into a lot of these topics. I would be happy to come back and potentially talk a little bit deeper about one or two of these at a later time. But my hope is that this sort of broad brush introduction gives you a good understanding of different ways in which industry is using some of these capabilities going forward. So should be no surprise. I don't think anybody would argue that geography is really becoming ordinary. Look no further than the phones in your pockets. All of us have map applications on our phones. All of us are using geospatial and geography for a variety of different things, right? It is used to help deliver your Instacart groceries. It's used to certainly navigate from here to the closest Starbucks. We use it, Amazon uses it, right, to deliver their packages. Geofencing now tells us, I don't know if you experience the same thing, but I now get alerts on my phone that tell me my packages are 10 stops away, right? So being able to use geofencing to obviously calculate time of arrival. So no surprise that geography and mapping in general has become a part of our ordinary everyday lives. What is probably a little less ordinary is the thought process that goes into how all those things actually happen, right? How many people are really understanding that Dijkstra's algorithms used to understand best possible routes along roads and things like that. There aren't a lot of people who put a lot of thought into the back end side of it. And really that's where all the interesting work on the geospatial side lives, is that back end processing of mass quantities of data that give us the answers that we need. We are quickly now, we're living and moving into a world that relies on what we call live location. It's not good enough to have just static maps anymore. It's becoming increasingly important for us to take dynamic information, update those maps as we go, and leverage that live information to answer better and more specific questions as we go. We've been working towards this for decades. I'm a college-trained geographer. I was one of the last groups at Penn State to actually learn lithography, etching in copper and inking paper. One of the last to really use Adobe Illustrator to do cartographic finishing and label placement before that all became part of standard GIS workflows. So I definitely have a very good understanding of the way things were done. What's interesting is how we've moved forward, and the natural progression of using desktop GIS to do your analytics and to create maps, the movement to web mapping that happened in the early 2000s with Yahoo Maps and Google Maps certainly made geography more accessible to more people. And nowadays, as we've talked about, right, maps are on our phones and pretty much go with us wherever we go. What's interesting though is that final step and how we're applying AI and ML to process that mass quantity of information coming from IoT sensors, from all of our cell phones constantly as we move throughout space and time. We're on the cusp of something really remarkable. And we're going to talk today about some specific examples of folks who are doing some interesting things using all those technologies. So let's start with sort of thinking about remote sensing and satellite image processing. Now, I don't know how many people knew this or not, but this past week, we actually celebrated the 21st anniversary of the first commercial satellite image to really be sold publicly, and that was the Iconos satellite. The first image from Iconos came out in October 12, 1999. It was essentially a shot of DC, and it actually made the headline of the New York Times on that day. It was a big deal, right? Satellite imagery being sold commercially, available commercially to anyone who could afford it. That was a massive, massive step forward in our ability to work with remotely sensed data. It had a massive coolness impact, but it also opened up a ton of questions about privacy and safety concerns, and what is it that the imagery could actually take pictures of, and can it read my newspaper, and all these sorts of things. Obviously, a lot of that's been worked through as we go on. But what's interesting is just several years later, this is 2008. This is the GOI-1 image, the very first shot that came from that satellite. You can tell a big difference, right? The Iconos satellite, it was a monochromatic photo. This is a multispectral photo. The resolution increased by 100%. It went from about 1 or 1.5 meters to almost half a meter, 50 centimeter in this case. Massive increase in capability in less than 10 years. And so if you think about it, we all kind of took this for granted, right? Technology gets better, we can collect better data. What you're not necessarily thinking about, though, is all the back-end processing that had to increase in order to allow for this to happen. So organizations like Maxar, which at the time was Digital Globe, had to basically create a giant supercomputer behind the scenes to process the amount and the volume and the size of all of this new data coming off all these new sensors. You know, you went from single banded to 4-banded to 8-banded very quickly. You go from bit depths, which were, you know, 2-bit to 8-bit to 16-bit very quickly. And so the size of each image, you know, certainly ballooned. The amount of imagery being collected by the additional satellites being put up in space ballooned. And so what's interesting is these supercomputers that were created needed to process more data than ever before. They quickly realized that they hit a cap. There was only a certain amount of processing that could be done with physical infrastructure. And organizations like Maxar started to look in a different direction. One of the things that Maxar did was actually partner with AWS. You know, the power of the cloud, I don't think needs to be explained to anyone on the call, but what's really interesting is when you start to measure the efficiencies and the return on investment of cloud computing and high performance computing, what are some of the actual quantitative advantages you can see? In this particular case, Maxar did a test with AWS. They transitioned to AWS's high performance computing cluster. They were able to see effectively a 58% increase in performance over their sort of homegrown local supercomputer, but leveraged 45% less computing resources, which to a company like Maxar, who's looking at, you know, imagery at scales that we can't even imagine, you're talking about millions and millions of dollars in savings, that 45% increase or decrease in compute resources. So this transition was a big deal. And that transition was largely due to the ability of machine learning to automate the processing that was going on behind the scenes. You know, what kind of processing are we talking about? You know, everything from orthorectification and atmospheric corrections, pan sharpening, and everything in between. Things that could be done by humans, but the volume and the scale at which the imagery was coming in, it was impossible for them to keep up. Now, compare that to Planet Labs, and a lot of people have heard of Planet. Planet Labs launched back in 2010. They basically had this notion that they were going to image the globe every day. And if you think about that, right, collecting a image of the globe everywhere on Earth once a day is just mind-boggling, right? If you think about the benefit that brings, though, right, you have an unprecedented view of the Earth and how it's changing, when it's changing, and where it's changing, that you can literally go day by day and show quantitative metrics for. Today, there's about 150 or so, slightly more, planet small sats that they call them. They also call them nano satellites, if you're familiar with the term, that orbit the sun, orbit the Earth, sometimes imaging the Earth up to twice a day. So we're not even talking about just imaging the Earth once a day. In certain cases, they're actually hitting the same spot on Earth twice a day. And that's just, again, phenomenal if you think about the refresh rate there. Planet owns and archives and maintains, you know, a ridiculous amount of imagery. I've heard it's up to 15 petabytes of imagery, most of it greater than 3-meter resolution. Anybody who's dealt with remotely sensed imagery in a GIS knows image files can get huge, right? Several megs to several gigs in size. And you're collecting all of that for the entire globe every day. It's simply massive. And again, it's going to take something beyond a manual process to really handle that. So that is the challenge, of course. How do you begin to process that volume of imagery? Now, Planet sells subscription services to its imagery. It certainly makes money by selling access to pixels. But not everybody has the expertise to turn that data into insights. And so Planet learned very quickly that they were going to need to do more than just sell imagery. They created a platform and a set of APIs that they call Planet Analytics, and this was launched a couple of years ago. And that's effectively a set of computer vision algorithms that run behind the scenes against this mass quantity of imagery collected every day and begin to derive insights, right? We're going to monitor the Earth daily. We're going to look for trends. We're going to be able to give that information to people who may not be smart enough to necessarily understand how to derive that from imagery, but we can ask a question of that archive and get a response in a very Google-like way, right? Where are we seeing the most urban growth? What do we estimate population density is over a certain area, and how does that compare to 10 years ago? Because they have this massive archive, they're able to use machine learning to process that data at scale, be able to look back and provide those insights in a much easier way than they have been before. Planet today, again, I mentioned, is about 15 plus terabytes every day that they're collecting. It's truly astonishing. If you think about it, as denoted here on the slide, they have this fast track capability. And that effectively gives users the ability to access imagery within 3 hours of acquisition. And again, I don't know how much knowledge everyone on the call has on remote sensing, but that's truly amazing, right? To be able to take an image from raw format, perform all the orthorectification, right? Remove the geometry from the sensor, get it to be true nadir, perform radiometric and atmospheric corrections, right? Remove all of the noise from the photo, do any post-processing, pan sharpening, other processes that are common for imagery that we see today, and do all that within 3 hours, right? It's truly astonishing. And I doubt anyone would be able to do it at that scale, 15 terabytes every day, being able to manually, right? Without the use of high performance computing and machine learning to automate some of those nonlinear processes that have to go across each pixel. So it's really interesting to see what they've done. Beyond sort of just remote sensing and imagery in general, the next logical progression, of course, is derivative analytics. I don't know how many people are familiar with Ecopia. Ecopia has been around for a while now, 2010-ish, I believe, is when they were formed. But their whole mission is to digitize the world using AI. They've formed really unique and interesting partnerships with imagery providers, such that their AI technology will use all of that imagery to create high definition vector maps of the world. What do I mean? They're really performing what we would call feature extraction. And I'm not in any way, shape, or form belittling feature extraction. It's an extremely hard concept to perform correctly. But that is the core of what they do, is they're taking imagery, they're using AI, they're using computer vision to scan through those images, find regular patterns in that pixel matrix, and be able to extract what they know in a meaningful way. It goes way beyond that. And to give you some sense of how important this mission really is, NGA, which is a term some of you may be familiar with, the National Geospatial Intelligence Agency, they're the largest geospatial user and producer in the federal government. They spend about $1.92 billion every year on contracts solely devoted to feature extraction. Now, the feature extraction is used in everything from creating maps over areas where we don't have new data, areas we can't go because of conflict or danger. They use it to find vertical obstructions for takeoff and landing of aircraft and new buildings that go up and how that affects flight lines and things like that. It is a constant challenge to continue mapping the world repeatedly as the world continues to change. And leveraging automation and machine learning and computer vision against imagery is the only way that we can really keep up with this. You put 100 analysts in a room and ask them to kind of replicate what the machine learning is doing, there's no way they're going to even come close. It's just not possible. In 2018 is a great example of this. Ecopia partnered with Digital Globe. Digital Globe effectively gave them access to every piece of imagery they had over the United States, and basically said, we want to try and create the world's most complete building footprint data set. They were able to effectively look at and create 169 million buildings over 9.8 million square kilometers, and did that in roughly 6 months. This is not just sort of rough cut footprints, right, that have been sort of done roughly or fastly using machine learning. These are very, very accurate building footprints that have straight edges, 90-degree corners, that have been aligned to streets properly, that have been offset from the roads properly. This is a massive undertaking that leveraged a huge infrastructure, again, using AWS because of their cloud compute resources, but just a massive amount of compute resources to get right. The fact that it only took them 6 months to do effectively every building in the United States is truly amazing. Now, you may say, oh, well, OpenStreetMap and others have sort of global building data sets as well. And you're right, they absolutely do. However, what sets Acopia apart from, let's say, your OpenStreetMap is the way in which they're using that machine learning to go a step further. One of the things that they've done is actually include detailed address information, detailed metadata and attributes about the buildings themselves that go beyond just a footprint. So you're talking about things like area codes and zip codes that are based on a lookup from other vector data sets. We're talking again about building centroids, moving the geolocation point from the actual road to the center of the building. You're getting building level geolocation now. In certain cases, these companies are working with micromobility. So I think scooters and delivery, Instacart, that kind of thing, last mile delivery, to actually include things like delivery points on buildings, right? You see signs, deliveries go to back. We're getting to a point now where your Instacarts, your FedExes, and others need to actually know where the delivery points of buildings are, not just where the entrance or the building or the geocoded centroid of the building is. So they've taken the time to put that in here and really differentiate themselves from something like an OpenStreetMap. And all of that is entirely due to the ability to use machine learning to automate this very complex, non-linear function. Another great example of that is Orbital Insight. And probably a few, if not all of you, are familiar with Orbital Insight. They too have been around since about 2013-ish. They have raised $128 million through 4 rounds. They closed their $50 million D round in November 2019. They exist solely for being able to provide analytical services that derive information from imagery and help drive policy and economic trend decisions. It's a massive thought process that goes into how do we take imagery and make useful sense of it? How do we give NGOs and governments the ability to understand what's going on the ground to a level at which they can make decisions? That's sort of one thing, but then to have the accuracy and to have the fidelity and confidence in that answer to be right so that those policy decisions can be made, that's a whole nother level. And that's really where Orbital Insight is making a lot of their money and explains why their valuation is so high. Here's an example of that. It's a very simple and easily understandable example. Companies collect information all the time. Here we're looking at an image over an auto manufacturing plant. It's very easy for the human eye to understand when we see vehicles, for instance, in the parking lot and when we don't. If you look at typical trends of any office space, whether that be corporate or manufacturing, you typically see regular trends, right? People are working during the week, they take time off on the weekend, and you can see that happen very regularly. But what's really interesting is over a week in May, we actually saw a shutdown due to COVID, very keenly and easily in the imagery. I've outlined that on the graph there in red. But it highlights very quickly and brings your thought process to, here's what I should care about. Here's the anomaly that I need to investigate further. It's not normal. What's interesting though is while any body, any human could sort of look at a parking lot and go, yeah, there's nobody there, there's something going on. The question I pose to you is how quickly could you count exactly how many cars are in that parking lot on any given day? And that's where the machine learning and the AI comes into place. Orbital Insights can actually take and mathematically calculate quantitatively the number of vehicles that are in a parking lot. Why does that matter? Well, if I'm, a hedge fund, or if I'm, a futures or commodities trader, I want to know, are there people going to Walmart or Target or these big box stores or not? How much of an impact has something like COVID had on the ability for people to go shopping? And how can we take that mathematical number of cars we see in the parking lot and equate that to an estimation of what we think earnings are going to be that year? So it's one thing to just note a trend visually. It's another thing to mathematically and quantitatively measure a trend and use that as a predictor in some way, shape, or form. And that's really what Orbital Insight does. And it does it in some very unique ways. Here's another example of some computer vision work they did over a construction site, very large, very expensive construction site. The heat map that you see at the top there is actually cell phone pings, the geolocation of cell phones as they attempt to reach their cell phone towers. In June 2016, they were doing some work, and it was a very big 250-acre lot that they were building on. There was lots of money. It was $3.1 billion that were invested into this project. And the people who were the main stakeholders basically said, we want to maintain eyes on the progress of this. We don't want to see it go slow. We don't want to see it go south. And they were measuring cell phone pings day after day. The two images you see at the bottom there are actually a sort of before and after picture of what the building footprint looked like as cell phone pings expanded throughout that 250-acre complex. And so it became very easy for their stakeholders to see, look, the growth is happening. And here you can visually see how that growth is happening by measuring where people are effectively throughout that complex as it grows and matures. And so Orbital Insight is a very interesting way of taking satellite imagery, taking other sources, in this particular case, geolocated cell phone information, and being able to display that in an interesting way. There's a whole wide range of use cases for this, right? Everything from real estate due diligence to insurance and flood mapping, supply chain monitoring. But really none of this would be possible without the machine learning that goes on in the background to help automate and facilitate counting of cars and numbers of ships that hit port. And there's all sorts of metrics that they follow to enable the type and level of detail that their insights unlock. And so very interesting use case. And that brings us to sort of live location data. Everything we've talked about so far can be done effectively, post-process, right? Something's collected, we go back and we look at what's been collected and we derive some kind of insight from that after the fact. But what about data that's live? What about data that's being collected and analyzed near real time? How does AI and machine learning play a role there? Most of you know who Uber is. I'm sure many of you use Uber regularly to get around. Uber was a complete market disruptor, right? When people think about the definition of a disruptor, that's really Uber, right? They came in, found a ton of shortcomings with the taxi industry, and basically created something from the ground up to basically overcome all those short challenges, right? And they were able to do it in a way in which was modern, that people could easily get involved with or started with. Very simple. Everyone has a cell phone. Mapping is an intuitive way to see how things work. Naturally, people tend to think of Uber as a rideshare company, right? It's how I get from A to B. But if you think about it, does that explain their $50 billion valuation? I don't think it does, right? I don't know I don't know of any millionaire taxi drivers, and I certainly don't know of any taxi companies that have valuations in the billions, right? So something else is going on there. It's probably better to think about Uber as a data company. Uber roughly serves about 3.1 million trips every day. And on each of those trips, it's collecting information beyond just where am I going? Of course, there's where your pickup point is and where your drop-off point is, but there's a ton of other information, right? How long did that trip take? Gives an insight into the traffic patterns at that particular time of day. Where are you going and where did you come from? And are those two things related, right? Are you going from the dinner to movies or vice versa? Are you going to get pizza and a movie, right? There's no more video stores anymore, but that used to be the big example, right? Did you go to the video store and the pizza store, get dinner and a movie to take home on a Friday night? It becomes really interesting when Uber becomes the data company that can give you insight into pattern of life of a geographic area. How transient are cities? Where do people migrate at different points of the day? They even capture your willingness to pay, right? You go to request an Uber and it says it's $37. That may be too rich for you, right? And you may deny the trip. They're logging that as well. They're capturing what the willingness to pay is for each individual user and assigning effectively scores to your social economic status and based on your geography, how willing you are to take rides. So all of that information being collected is what makes them worth $50 billion. they're using a ton of machine learning behind the scenes to really process that information together. You may have guessed it, but the map you see on the background here is an Uber map of, in this particular case, rideshare through New York City. But what you may not know is Uber had to create their own mapping library, their own mapping team in-house to handle the amount of data that they were putting through their system. There was no available API or SDK that could really handle the scale and the size and the complexity of that data that they were collecting. So you may be familiar with DeckGL, you may be familiar with KeplerGL. They're basically WebGL libraries built with JavaScript that enable you to do these unbelievably, really aesthetically pleasing visualizations, but also complex analytics all through a web browser. It's truly fascinating what they let you do. And they did it out of necessity, right? You always hear the necessity is the mother of all invention. Uber really had to do all of this themselves because there was nothing out there that could do it. Kepler and Deck are both open source libraries. If you are a JavaScript developer, I encourage you to go take a look at it. They've got some really interesting APIs that you can use to do some really cool stuff. Excuse me, SDKs to do some really cool stuff. Here's just a few examples of what Uber has sort of made publicly available, ways to analyze very complex data sets in a very easy to understand way. But the other example is certainly Mapbox. Ross mentioned a lot of you are probably using Mapbox. It's a tremendous capability. I enjoyed very much my time working there. What is interesting about Mapbox is they don't actually have or make an app of any kind. You think about all these Silicon Valley companies who make apps. We just talked about one, Uber, great example of a company who effectively makes an app and people interact with that app. Mapbox doesn't make an app. It's effectively a set of SDKs and APIs that allow you to make your own maps. That's really a different way of thinking about how to get into a customer space. Everything from chat apps to weather apps and everything in between, Mapbox powers a massive amount of user-focused applications all throughout the world. As of April 2019, they were roughly supporting about 640 million monthly active users. That means every month there are 640 million people using their platform. To put that into perspective, Twitter has about 300 million. So Mapbox more than doubles the amount of Twitter users on mobile devices alone. That's not even counting their web use and web applications, just mobile devices. They have about 1.6 million active developers who are continuing to enhance a lot of the open source code that Mapbox has made available. And through applications that are vehicle focused, and we'll talk about computer vision here in a second, they collect roughly about 320 million miles of road every single day. Now, all of that information is basically giving them an ability to do some really unique things. Now, what apps are we talking about? What are the applications that Mapbox is in? I would almost bet a paycheck that everyone, save maybe a handful of people, I could probably count on one hand, all of us have some app on our phones right now that is using Mapbox technology. Here's just a few of the more popular ones that you probably have on your phone, but you may not even know it. You're leveraging Mapbox's SDKs in those apps that are on your phone. From all of those apps, Mapbox is collecting anonymous live location information, which is powering some really interesting, what they would consider premium level data sets. Things like HD lane information. As autonomous vehicles become more and more important, they've got to obviously be able to self-drive. Having detailed information about each lane within a road, not just the center line, but each lane within a road, right? It needs that information to know how to navigate itself from, let's say, the left passing lane to an exit that happens to be 3 lanes to the right. That's extremely important. Footfall traffic. We commonly see this, if you've ever done a Google search for a restaurant, you'll see sometimes it shows you peak busy times, right? They call that footfall traffic. It's how busy a particular location is based on the number of cell phones and devices and people that are generally participating in being in that location at any given point in time. Mapbox obviously uses live location for its traffic information, right? The speed at which people are moving across road segments dictates how they colorize the map in terms of it being green, amber, or red for, obviously normal speeds, slowed speed, and particularly stopped or slow speeds of some kind. And many, many more. We'll talk about computer vision and signs and speed limits here in a second, but it is all a massive, massive amount of imagery, massive amount of data that's being collected every second from all those 640 million monthly active users, from all of those apps that happen to live on your phones. Now, I want to be very careful here. That sounds very scary, that Mapbox is collecting all this crazy information. They've done it in a very unique way that anonymizes all of that data collection. So Mapbox knows that a device is moving across a road segment, but it doesn't actually have any information about the device itself. And of course, to do all this anonymization, there's a whole set of algorithms and machine learning that run in the background to do that as well. How to describe that in a very oversimplified way, I'm going to attempt to do here, but I promise you it's a much more robust process than what I'm showing you. So let's assume you're going from, let's say, your house to the bank. You want to take out some money for the weekend. You get in your car, or you get in whatever bike or whatever rideshare system you have, and you're going to actually commute along roads to get from A to B. What Mapbox does is actually truncate automatically the first 300 and last 300 meters of any trip. And they do that so that they don't capture where you're coming from and where you end up. And this is really important to help maintain privacy of where you live and obviously where you work and where you go. They take that a step further. The next thing they do is they actually break each trip into segments that are no more than 5 minutes long, which means if it takes you 15 or 20 minutes to get from your home to the bank, it's actually splitting that entire trip up into 3 sort of mini trips. Each of those trips is given a unique ID. And so there's no way for Mapbox to capture in any way or tie together each of those individual road segments or trip segments into one long trip and say, oh, this same device started here, went there, and followed this particular path. It's physically impossible for them to reverse engineer that trip to know that. So no identifiable information of any kind is captured, no cell phone numbers, no ad IDs, nothing like that. What they simply do is take the fact that a device that existed moved from space A to space B. It took them some time to do it, and that time is what they use to actually calculate the traffic patterns. This is giving them a hyper-local understanding of how quickly people can move. Where are there road closures? Where are there slowdowns? Where are there incidents that may be causing traffic jams to occur? And this is all being processed by a massive AWS-based high-performance computing cluster behind the scenes. It is constantly being updated. Mapbox has hired privacy engineers, to make sure none of this is reverse engineerable, but it's given them the ability to have a leg up on a lot of competition because they now have hyper-local, hyper-accurate information about how people are moving through space and time at any given point. But Mapbox actually doesn't stop there. You may be aware of their Vision SDK. The Vision SDK is, as the name implies, a computer vision SDK. It is what's giving them the ability to take any camera device, whether it be a dash-mounted webcam or vehicle cam, or the camera in your phone, a commodity device, and be able to do computer vision and scene segmentation locally on that device. Now, this took them many years to develop. I was there for about 2 years, and in that time, they spent one of those years simply working on battery life and how they could take a commodity device like an iPhone or an Android phone, do computer vision at the edge, but save the battery life and not cause the strain that other AI and computer vision systems were causing, which made them effectively rendered unusable. And so it is truly amazing what they've been able to do. What are they doing with it? They are going after the autonomous vehicle market, right? They've created, and again, there's plenty of videos you can see on their YouTube page and their Vimeo page about how some of this stuff works, but it's really fascinating. They've created sample applications that show how their SDK, in this case, the Vision SDK, in combination with their navigation SDKs, can be used to do things like autonomous vehicle routing. We talked about the HD lane information. That top image there shows you just how the routing engine would actually show how to move over within a lane to get to where they need to go. The second image actually shows you how the computer vision segments to identify objects, in this particular case, a bicyclist, and would actually cause or tell that autonomous vehicle to start braking. And then, of course, many of you have used Unity and other AR and VR platforms. Mapbox has a Unity SDK, and you could do things like this immersive example here at the bottom. Being able to put you in the center of the map and have information pop up around you that may be relevant to what you're looking for. So they've really taken computer vision and computer vision at the edge to a whole new level, really focusing on the hardware aspect and understanding how to preserve things like battery life while still showing the performance that is needed to make computer vision really, really important and powerful. And then the last but most advanced sort of use case I wanted to talk about today was actually custom AI. I'm very fortunate enough to work for Enview, a very custom 3D AI company. And it's given me some really unique insights into how machine learning and AI really gets applied to mass quantities of data. So I hope most of you are familiar with LiDAR, light detection and ranging. It's gotten a lot more press over the last week with Apple's announcement that LiDAR sensors are now going to be on iPhones. They were actually put onto the iPad last month when they released new iPads. But LiDAR is unique for several reasons. Number one, it's a true 3D data set. It's also collected as point clouds as opposed to flat images or 2D data of any kind. It's collected as a 3D point cloud. To give you some context here, a linear mile of LiDAR is roughly anywhere between 2 million and 250 million points within a linear mile of LiDAR. It's massive, anywhere from 3 to 4 gigabytes in file size, but just literally millions of points within that linear mile. But it gives us tremendous insight. LiDAR, unlike imagery, preserves the geometry and the shape of features. So, for example, if there was a tank camouflaged underneath trees or camouflaged underneath some netting, we may not see that tank in visual imagery, satellite imagery. But with LiDAR, you actually get the true shape of the object in 3D. The camouflage is irrelevant. It's hard to hide a 70-ton tank, right, from a geometric collection of 3D data. And so very unique in that aspect. It's also unique because from one file, you can get many different insights, right? The example here, we've sort of segmented a piece of LiDAR where you can see the vegetation layer, but you can also turn off the vegetation or remove it in a way where you can see all the objects below. This concept of first return versus last return or bare earth, and these different returns that come back from the light sensor, the laser sensor on the LiDAR camera itself, gives us the ability to peel back layers of elevation and kind of see what's underneath. Slope and hillshade and terrain analysis, building facades, detailed structure layouts, they're all unique and a value add that LiDAR gives that you can't necessarily get from imagery. The challenge, and despite the many benefits of 3D point clouds, they're incredibly difficult to process. They're huge, right? I mentioned both the file size and the number of points. But more importantly, traditional AI does not work in a 3D space. So if you think about it, TensorFlow and other sort of 2D centric AI platforms were trained against 2D models. In a lot of cases, imagery, right? Acopia, the Digital Globe and Planet use cases, they're all image use cases. They're all leveraging 2D imagery that has a regular set of pixels. Each pixel is the same size. You know how many neighbors are going to be around that pixel as you move throughout that pixel space. All of that's very defined and regular. When you talk about a 3D point cloud, it breaks all of those assumptions. 3D point clouds are completely irregular. There's no set quantity of nearest neighbors. It all depends on how dense the LiDAR sensor is. And there is no regularity to a point cloud at all. So when you take a 2D AI and try to apply it to a 3D data space, it just simply doesn't work as well. So what's interesting about Enview is they actually took the approach of building a custom convolutional kernel designed specifically for 3D point clouds. and designed it from the ground up. Everything about this AI is unique and custom. They've actually taken it so far as to begin to think about sort of cascaded ML and cascaded AI frameworks, where depending on where I am on Earth, we know that there's unique characteristics there that don't live or exist anywhere else. And so we have to actually use a custom AI or a custom machine learning process trained at that particular area to get the most accurate answer possible, not just a generic one that is useful sort of 80% of the time everywhere. And so that unique cascaded workflow is what's given Enview the ability to process data with a higher accuracy and higher speed in a 3D world than applying your traditional sort of 2D AI to the same data sets. If you're not familiar with LiDAR and sort of how it works, here's just a very, very quick example. This is an unclassified point cloud. What the technology does is effectively looks at each pixel, applies the AI, applies those custom convolutional kernels, and basically says, these groups of pixels represent buildings, these represent trees, these represent other features, facades, power lines, vehicles, you name it. This process of classification and segmentation is really where the power of that 3D AI comes in. From this, there's a whole bunch of derived data sets that can occur, simple object detection and feature extraction, right? We talked about 2D feature extraction with Acopia. Here's now 3D feature extraction, going beyond just building footprints, 3D geometries of buildings to include all the textures on the roofs and things like that, the facades and the walls, being able to do change detection. If I have point clouds from 2 different time periods, the AI can be used to detect the change between those 2 clouds and be able to highlight areas of significant change, right? Think terrain events, mass wasting events like mudslides and earthquakes, landslides, all those types of things. And then to do things like vegetation mapping. I didn't realize it before I started working in the space that vegetation management is a multi-billion-dollar industry. Power line companies must, by code, trim back vegetation within a certain distance of power lines to prevent wildfires and other things from happening. And this is a massive, massive industry that relies on manual labor to go out and visually inspect hundreds of thousands of miles of power line and pipeline. Using an automated process like this, where machine learning can cut that time down to hours rather than months of manual work, is showing a tremendous return on investment for those organizations that need to manage hundreds of thousands of miles. Great example of that, here is a LiDAR that was used by a pipeline infrastructure operator. They've got several thousands of miles of gas pipeline in California. What you're looking at here is very simple image collected via satellite. What you're looking at, it's hard to see, but there's a pipeline in blue that kind of goes through the middle there. So this is sort of time A or before. Now this is time B. You're probably going, I don't see a ton of change there. And you're right. Other than things like shadows and maybe some atmospheric haze, there really isn't a lot of difference between the 2 time periods. Certainly some vegetation has grown, but no significant change is visible here. If you were reliant just on visual detection and imagery, you wouldn't notice something very significant that was determined or depicted in LiDAR. And that is the landslide that occurred very close to the actual imagery. Now, I assure you, all of these are the same time frame. There's no trickery here. But the before and after are just simple visual imagery. The bottom image is a LiDAR graphic or a LiDAR picture. It's a terrain surface derived from a LiDAR point cloud. And the coloring, the red and blue, denotes it's what's called a 2-color multi-view, where red is fled and blue is new. So red is, in this particular case, terrain or soil that was there at time A, not in time B. And the blue represents stuff that was there at time B, but not at time A. And so naturally, what we see is a shift of soil or terrain from one point to another, representative of a landslide. Now, this event, this rupture here, if it were to rupture, is a $50 million event, not to mention an environmental disaster, and that's not accounting for any potential loss of life. And so detecting what we call geohazards, or events like this, that could potentially be detrimental to a pipeline or a power line, is extremely important. being proactive in identifying these things before they happen is a massive resource savings for these types of pipeline and power line companies. Using machine learning, using those convolutional kernels to create this sort of unique 3D AI gives companies like Enview the ability to depict those things, calculate those things in a much faster time frame than they could before. To put some numbers on this, this particular company would send out helicopters to do aerial survey and then manually inspect those thousands of miles of pipe. It literally took them 3 to 4 months to do this. In the matter of 2.5 hours, Enview was able to take the data set, run it through its neural net, basically pull out areas of interest. There was about a dozen in this particular case, and sit down with an analyst same day to say, here are the areas that you may want to focus in on. And again, it's solely that high performance computing and AI that allow them to do that. So I hope that those are just a few examples of the ways in which the industry has really shifted, right? We started in paper maps, we went to web maps and desktop GIS, and now we're sort of embracing this idea that there's so much data, we can't possibly manually characterize or analyze any of that ourselves. We are increasingly turning to machine learning, high performance computing, and AI to help us. The volume of data, the speed at which we need to process that data, the requirements for that keep going up. And the only possible way we're going to stay ahead of that is to leverage those technologies. Computer vision, machine learning are certainly two of the top. As we look at things like smart cities and how interconnected IoT sensors between different segments are going to be to enable smart cities, this is just going to become more and more of a challenge. And I think we're going to rely more and more on machine learning and AI to help solve it. So I thank you for your time. I hope this was useful. I wish I could go deeper on each of these, but hopefully this was a good introduction. And depending on how much time we have, John and Ross, I'd be happy to take some questions.
Oh, wow, thanks, Anthony. That was an incredible overview of what's happening in the geospatial industry. I think one of our participants said it best. This is eye-opening. Cool.
I'm glad somebody liked it.
I don't think it's common knowledge to know exactly all the financial models that are going on behind the scenes of what's driving everything. And yeah, thanks for sharing all that with everyone.
Yeah, it's really amazing, I think, to see the application of the AI, right? Or the machine learning or the computer vision, whatever the case may be. It really has, to your point, unlocked a different set of business that wouldn't necessarily be there before. And, I think the Orbital Insight use case is the easiest one to understand. If it weren't for those technologies, quite frankly, those companies wouldn't exist, right? Planet collects way too much data a day to be able to exist without it. And so to your point, these things really do unlock business use cases.
Cool. Well, we have about 8 minutes for questions and discussion. I see we have a question from Chris Jones. Chris, I'll let you speak up to ask your question, if you're there.
Hi, yes. So great presentation. And I was wondering what role you see a company like SafeGraph playing in this kind of pipeline. So they're doing similar things to some of the stuff you mentioned with Mapbox. And also, what role do you see coupling some of the work you're doing at Enview with some of like the traditional ML pipelines to map species distributions?
Yeah, great question. I know Aaron at SafeGraph. He's a tremendous guy. I love the company. I've had several interactions with them. They do really amazing stuff with, again, hyperlocal data collected from cell phones and computers and other things. I think what's interesting about SafeGraph is they have a wider variety of sensors that they're pulling from. If you think about, Mapbox focuses on the SDK that is on devices, right? The apps that are built with their SDKs. That's their source of data. A company like a SafeGraph can aggregate from more sources than just sort of their own unique SDK. So while I think maybe the analytics is similar, right? Being able to derive insights and pattern of life, I think one of the advantages SafeGraph has is they're collecting from a larger source or set of sources And sometimes that gives them a leg up on some of the other systems that are out there. And then your second question, how does sort of 3D AI maybe differ and provide a competitive edge over some of the other things that are out there? Again, right, the AI is only as good as how you train it. I think most people hopefully are aware of that, right? These systems don't just work out of the box. You must train them to understand what to look for. I do see a uniqueness in what Enview in particular on the 3D side has done, because they're not just taking off the shelf AI and sort of training that. They've actually taken the time to build a unique one from the ground up that was designed to work within the unique constructs of 3D data. I think that definitely has given them the ability to have more accuracy and more speed. It doesn't mean that others won't attempt to do the same thing, but I think that they've definitely certainly were first to market, and certainly have learned a lot of lessons that can be applied with other forms of data going forward. And just one other quick anecdote. One of the unique things too that I think Enview has over some of the other AI that's out there, they're going beyond just traditional, what's called linear mode LiDAR. They're also working with other modalities of LiDAR, which are collected very differently and have a different structure. Geiger mode, terrestrial, mobile, they're all different forms of LiDAR. And to be able to handle all those different sort of sources and forms is also very unique and interesting.
Thanks, Anthony. Looks like we have another interesting question from Tom Worm.
Yeah, thanks so much for the talk. That was really interesting. That was great. I had a question about how you saw the future of privacy with regard to these companies that are aggregating geolocated data. We've seen some good examples of how to deal with user privacy through Mapbox, but we've also seen examples like Uber's GodView, where they were using it as a party trick to locate people at the parties. How can we be sure as the users that may or may not be willing participants in this data collection that our data is in fact anonymous and not being accessed on the sly in the background?
Yeah, great question. Two-part answer. I think number one, I didn't even know privacy engineers existed until I spent my time at Mapbox. It's a real thing. This is a real problem, and there are professionals now that can help organizations craft pipelines that will ensure privacy. I was very fortunate that Mapbox was one of the companies that certainly employed them and added that to the process and workflow. But I think the second part is, interestingly enough, California, through some of the California data laws, is really the first to wade into these waters. The whole opt-in versus opt-out thing, right, where California's basically said, you must opt in to data collection as opposed to it being the default on and you opting out of it. I think that's a tremendous step forward. It's forcing companies to disclose more about what they're doing with your data. I would be shocked as an industry sort of insider if that does not follow into the remaining 49 states over the next 2 to 3 years. I think most companies must and will be forced to opt in for things like that.
All right, we have one more question from Ellie Cardinal, and she let me know she doesn't have a mic on, so I'm going to read it for her. So she said, I really enjoyed your talk. I have a question about how AI and machine learning have built-in biases. They have the biases of the builders, right? A specific example she's thinking of is a company that developed an app to track potholes based on car movement, vibrations. Public Works on the municipality ended up only fixing the roads in higher income neighborhoods because poorer communities don't drive to work, they walk or take public transportation. How do we prevent or account for this in development or proposal?
Great question. I think the answer, wearing my sort of VP of product hat, is product testing, right? It's great. What do they say? The best laid plans of mice and men often go awry. It's true. We've come across assumptions that we've made on a product side where we've developed something only to get it out into the field and realize we got to start over, right? We've totally missed the boat. And so I really do think that's where the product testing comes in. Really excited that companies like Mapbox and Enview and Planet, they hire data scientists, they hire AI and ML engineers to think through many different aspects, but then they're smart enough to take that thought process or that sort of experiment, put it in the hands of the product engineers to really facilitate the testing. There's no other way to catch that than to do that type of testing, really. there's no possible way we could think of all the eventualities and possible avenues unless you do some real world user testing. And that's really where product comes in.
All right, thanks. Well, I see we're at the end of the hour, so I'm going to close questions in respect of everybody's time. John, do you have any wrap-up announcements?
No, I do not. I just want to thank everyone for attending, and special thanks to Anthony for the fantastic presentation. Really learned a lot. Appreciate it.
You're very welcome. I appreciate the opportunity to present. I hope everyone enjoyed the talk, and look forward to doing these again.
Yeah, super. Thanks, Anthony.
Thank you, everyone.
Great presentation. Thank you.
I just